All right, so quick introduction here. First off, thanks everyone at vNYNOG and vNYNOG for giving us the opportunity to speak today. My name is Greg Villen. I work for Kentic. I'm on the product side of things, but I'm also a classically trained network engineer, although it's been a while since I've been allowed to touch a router, and it's probably for the best. You can find me on Twitter. I'm Greg with 5R, so nobody can really find me. And Kentic Inc. on Twitter too. So today I'm going to talk about modern day network analytics for data-driven interconnection decisions, which is a very long title. Apologies for that. So let's get started. And so a ton of what I'm going to show here is going to be sourced from what my company is building, but I don't want to focus on that. I want to make this a more informative than salesy talk, obviously. So it's the engineer talking more than the product guy. And so the first question legitimately that I wanted to answer is, why do people interconnect? And as stupid as it may be, it's a good driving guideline for the rest of the presentation. So we appear mostly for cost reasons, for performance reasons, and for path diversity resiliency. And so one of the things that'll come back quite often in this presentation is that interconnection in general used to be a much easier thing to evaluate back in the day. And I'll try and explain why to generate discussions around that. And so the first thing that I wanted to do is kind of like try and look at back at my days as a network engineer that would try to get whatever network interconnected that he was working for. And I try to take a look at the shortcomings of what was available out there for me to do that job of evaluating interconnections. And so the first thing is that none of it back then was real time, hasn't changed much nowadays. None of it was self-serve, meaning that anyone who wanted to get that information needed to ask a network engineer to obtain that data, and that was raw data. And so since it was raw data, a ton of spreadsheet wrangling eventually was involved here. The other thing is that that data was raw, it came from routers, switches, you name it, but most of it didn't have any coloring when it came to the business logic behind that traffic accounting data, and it wasn't really aware of connectivity and such. And also the path visibility of it was kind of weak because it was the early days of flow analysis, and path visibility wasn't like a huge thing back then. And so we had the premises of it. It was mostly a source ASN, test ASN kind of paradigm back then. And so, as I said, edge visibility mostly. So all in all, it wasn't very holistic. Most of the time it was reactive more than proactive. At best, it was in a review mode where every now and then we review the state of interconnection and be like, oh, okay. So, but in general, we'd take care of it when a pipe was running hot, which is probably not the position you want to be in. But worse than that, as I said, since it was not self-serve, the information was fragmented in a ton of different silos. Like the salespeople knew who the customers were and the associated ports were and such. The network engineers could get that data. The finance guys could mix and match the data to try and get some kind of ROI indication on what that data means. And so these are kind of like a summary of all the things that kind of got in the way to do it efficiently back then, and still quite a bit to a large extent nowadays. And so what does your network data get you today for you to do that job, that interconnection analysis job? And so, yeah, you get some amount of source destination ASN, some GeoIP, maybe if you're lucky, router breakdowns, some AS path information, but that's kind of about it. And kind of what I'm hinting at right now is that clearly not enough given the changing landscape, and I'll talk a bit more about the changing landscape. And so let's start with the first item that we had on the list. Let's talk about cost. And so in that part, I'm going to put myself in the shoes of a transit provider. And so one of the things that's important as a transit provider is, how do I know how much I should sell megabits per second to someone? anyone, any network that knocks at my door or any existing customer, how do I know how much they cost me and how much I'm selling them? How do I compute my ROI? And so this is a very typical, simplified, dumbed down example, because I'm a product person, keep that in mind. I'm looking at the ROI for a given customer, and everything here is anonymous, so I think we're on the safe side. And so I've got this customer that's connected to my router one here, and he sends a bunch of traffic through my network, and that can go both directions. And so I've got interfaces that traffic exits towards. I've got an interface that I connect this customer to, and it transits through my network at a variable cost. And if I look at the overall traffic for that customer, there's some stuff that exits on the same router, so and to another customer, so that's financially juicy for me. So I put a ton of dollars here. Some of it crosses my entire network to go to another customer, still interesting, but then transport is an additional cost in there. Some of it goes through my network and goes through transit, which means, well, not only do I have the transport cost, but on top of that, there's transit that I pay for it. And some of it goes through paid peering. And you see there's a range of costs involved depending on where I convey it to, where it exits my network, and what type of connectivity it exits my network with, all making for a pretty complex financial picture to get. And so the one thing that I want to get to is everyone trying to do that exercise needs an instant and precise picture of where it comes in and where it comes out of, with the additional dimensions of what customer we're talking about and what type of connectivity does it end up with. And so that's the math slide that's supposed to make me look smart. But basically, at the top of it is an even more simplified version of the previous diagram. You basically have one customer on one end. The orange is the connectivity costs. The blue part is the transport. And basically, your cost means that it's the sum of your connectivity costs on both ends and the sum of your transport costs throughout your network. And so obviously if your cost is positive, then it's cost of goods and services. And if your cost is negative, then it's revenue. And I think it's important for any network transiting data to be able to compute that quite efficiently, but also put them in the hands of another silo than just the network engineer that has access to this data. And so I'm looking at some random data from some anonymized data here that I did doctor a bit. And so you'll see here instantly on this representation called the Sankey. So I'm looking at all the sites that I'm connecting you with one specific customer to, and I need to be able to do that with all of my customers, which means I need to be able to define who they are and where they connect. And so some stuff goes from Dallas to Dallas, so it's hot potato routed, and it ends up, you'll see the last block in a Sankey is the connectivity type. It goes through a PNI, so it's fairly financially interesting for me as a transit provider. Some other stuff goes from San Francisco to Sao Paulo in Brazil through a PNI, so I still have the cost of transport that's not neglectable. And then some of the stuff goes customer to customer, Washington to Washington, which is the most ideal financial case for me as a transit provider. And so all of that to say that knowing where your traffic comes in and where traffic gets out, which means going beyond the plain edge view of your traffic, is kind of pretty important if you want to compute ROI data. And so one of the other elements here that I like to spend a little bit of time on is that the landscape of interconnection in general has evolved quite a bit. And so I'm going to go through a quick State of the Union here to try and figure out what's changed and what the impact has been on our ability to do our interconnection assessment work well. And so, as I said, the landscape has changed. The tools haven't changed much. They have changed a bit, but they haven't changed much. And so the result, and where I wanted to get to throughout the presentation, is that oftentimes networks have a very fragmented view of their traffic and therefore kind of suffer from a lack of analytical paying decisions to an extent that it's more an art than a science. And as a science guy, I like science better because I can understand it. And so if I could extract two main things that have changed recently or throughout the past 10 years or so, as 20 years or so, is the prevalence of CDNs and OTTs. And so CDNs, I probably don't need to explain what these are, but OTTs commonly refer to over-the-top traffic, which is basically all the apps that you consume that are not provided by your internet service provider. So this is not your IPTV, this is not your voice over IP service. This is your YouTube, this is your Netflix, this is your Spotify and such. And so these things have had a huge impact on networks' visibility of traffic and ability to do interconnection well. So I'm going to spend a bit of time on it. So the first thing is CDNs have become the new norm. Most content providers rely on them. There is no large content provider that doesn't leverage some form of a CDN. One of the things that's slightly that makes things slightly difficult is that all CDNs are not created equal. And by that, I mean, each CDN delivers traffic over a variety of different types of connectivity into your network. And I'm gonna get myself in the shoes of a residential internet service provider here for that purpose. And so peering-wise, these CDNs, they basically stand between the ISP and the content provider, adding a new set of people to talk to whenever you're considering interconnection. And that makes it very different from what it used to be, whereby an ASN was the source of, the unique source of some amount of content, of a specific type of content, and it was easy. You would just look at ASNs and know what you had to do to interconnect. But CDNs have made this much more difficult to grasp, I'd say. The other thing is the era of the seamless network is kind of over. Everything now is pretty much an overlay. CDNs are the best example of what an overlay can look like. And so one of the difficulties here is that there's no real native network visibility attributes to associate CDNs with the traffic that comes in and out of your network. And as I mentioned before, the plain ASN view doesn't make a ton of sense anymore. And we've seen, as we've seen in a recent, I'd say 10 years or so, last mile cache embedding has become one of the main realities. So I'll get back to that. And so these are like, just to show the prevalence of CDNs, this is some random ISP somewhere, 94%, and this is kind of like the same across across the board, as pretty much more than 90% of an ISP's inbound traffic usually corresponds to CDN, whatever form of CDN it is, and I'll get back to that. And in that case, you'd see that nearly 80% of that ISP's traffic comes from 5 CDNs. And the amount of CDNs out there and their footprint varies very differently. Here I have 52 at the time the screenshot was taken, but we're probably nearing 60 now, with all kind of global versus regional kind of different spreads here. And so everybody's seen that diagram a million times, but this is basically what in a nutshell, what a CDN looks like and how it interconnects in different ways, shapes, or form with an ISP, with the content provider being on the east side of the diagram, serving as the origin of content. They can reach the users, which are the orange pods on the left side, through a variety of means, whether it's from the origin itself, so hosted by the content provider's own infrastructure, through some caches in transit providers. Some CDNs run exclusively on their own infrastructure, which is the purple side of the thing. And some run on a hybrid mix of that. As I mentioned, also some amount of last mile embedding happens depending on a CDN. And the money flows are literally in every direction. The CDN provider pays transit providers. The ISP also pays transit providers. The content provider pays transit provider, but also pays CDNs to convey their content. We're using peering fabrics where both ends pay. And so it's a pretty like large map for people to fit in their head and apply on the fly to their traffic. And so let's go back to what we said very early on. Is like, let's look at cost and let's look at performance, because it's what we're interested in, and that's why we're here. And so I'm going to put myself in the shoes of a residential ISP here, and I'm going to look at traffic that comes from just, apologies, from just one single CDN. And so here's it's an actual picture, heavily anonymized, obviously. And so I've got nearly 50% that comes from embedded caching. I've got nearly 50% that comes from transit, a little bit of switch fabric, a little bit of PNI, and so all of these come with a different cost. That's the first obvious statement that I can make looking at this. The other statement that I can make is, how come do I have embedded caching and transit connectivity for the same CDN and in equal parts? One would think that for performance and cost purposes, one may favor embedded caches. So smoking in for something, that's a good thing for an interconnections person to look at. And remember, traditionally speaking, interconnection people initially didn't have the habit of looking at these types of embedded cache traffic because they just didn't exist back in the day, and they looked at pipes. And so this is one of the things here. And so still with that same CDN, let's look at performance. And by performance, I'm using a very simple proxy, which is the average bandwidth per destination IP. So I'm looking at exclusively traffic coming in or traffic coming in from the embedded appliance in the last mile. And I'm basically breaking this down by the different types of connectivity. So on-net embedded cache to the subscribers, the blue one. And the other three ones, the peering to subscribers, which is the green one, the switch fabric to subscribers, which is the red one, and the transit to subscriber, which is the yellow one. So now if you look at all of that in one single curve, it's not going to help you much. The second you break it down by type of connectivity, you learn some interesting things that you did not see before. There is some signal kind of hidden in the noise here. And so the first thing you notice that, yeah, obviously, embedded caching is more efficient than the other methods of delivering traffic. I'm not saying that the other methods aren't valid, because most of the time they do the job, but there's a noticeable difference in usage, in performance. And by performance, I mean average bandwidth per destination, unique destination IP. Now, here's the interesting thing. The second you lean on these graphs, bam. If I look here, at some point, sometime, something happened causing IX traffic to drop for that CDN. And so that's an interesting thing to look at, because on the other end of the phone, there might be a subscriber asking, why is my whatever video service rebuffering? And so that could be a smoking gun. So knowledge of this, whether it's proactive to make sure that this doesn't happen, or reactive to make sure that I'm able to give an answer to whoever's calling the tech support frontline, is pretty handy these days. And so still talking about cost and performance, you'll notice, as the previous slide kind of tried to outline, that for one single CDN, there's a variety of very different costs involved in the mix, and a variety of resulting performance. And so that was just for one CDN. Now multiply the noise in that picture by the number of CDNs used out there. And I'm, again, more than 90% of the traffic coming into an ISP comes from a CDN. We might have a visibility problem here. The next thing, so we talked about CDNs, but the next thing is really nowadays, if you're a residential ISP, you kind of need OTT service level visibility. And again, this is all about taking it one step further than the plain source and destination ASN picture. And so subscribers care about the OTT services that they use, right? Rarely do they call the hotline, the frontline tech support, saying, well, level 32's transit network or slow DR CDN is wrong. right? It's slow for me. No, what they call for is say, oh, damn, my Game of Thrones episode is rebuffering, that's unbearable, or it's taking me hours to download the last Call of Duty update. Well, that might be too soon. So subscriber performance in general, if you look at it, is a very powerful differentiator in a highly competitive and low margin business such as internet service. And maybe it's not as visible in the United States, where you have some form of geographic prevalence of specific ISPs per region, but in Europe, where it's usually easier to switch from one provider to another, this becomes a weapon of competitiveness, right? The other thing is that, well, performance has a cost. And if you want to do it right, you need to optimize the stuff that's more important first, and not spend time optimizing at great cost things that won't make a difference. And lastly, compounding all of these dimensions that I talked about previously, performance is, as we've seen, very different for each arrangement of OTT, POP, where the traffic's coming in, connectivity type on that POP, the provider involved. And so various stages of complexity interfere with a clear picture. And so one of the things that's, as I've been building products to do that, the main thing that often comes back is like in the break room of literally any ISP you've been working at or will be working at once in your life, someone will be saying, hey, we got these subscribers that are complaining about the performances of these video service. Would you remind me, do we pair with us? I rarely have seen anyone getting an immediate answer to that. And the reason is quite simple. So again, this is a fully anonymized view, but so on the left is all the traffic from that $video_service. Then the POPs it gets delivered from to the subscribers, then the type of connectivity involved, then the provider for that connectivity out of the router in that POP, and then the CDN that's on the end of that. And so that is a real life scenario of the picture for one video service. And remember, subscribers, they knock at your door saying, well, my Game of Thrones episode is lagging. It's rebuffering. I can't watch it proper. And so the view that you have on your traffic is really parasited by the amount of different subsections of this traffic. But more than that, it does get worse. It always does. That's the only certainty that we have here. And so now think about content releases over multiple providers. And by that, I literally mean over multiple providers, over content providers, over multiple CDNs, over multiple connectivity types. And so here's my inbound traffic. I'm a residential ISP. All seems fine, right? I mean, let's discard that bump here because it was something I knew about, but it looks fine here. Now let's drill in a bit, right? Now, if I break it down in types of content. And so that's an additional dimension that I'm introducing here that I'm positing we need to look at, is within that absolutely normal traffic here, I got a bump inside here that says that it's gaming traffic. So that's interesting because otherwise I would never look at it. If I had the ASN view of it, I'd see something with CDNs, but that's about it. Now I can go further because remember, there might be subscribers calling my tech support right now. And so let's dig into that bump because for now it's a mystery. I know it's gaming traffic. No, I can probably dig into that. And so I'm isolating everything else on the previous picture, and I'm just looking at the providers of that. And so I see a bump which correlates 3 major players out there at the same time, right? And so a bit of that is PlayStation, a bit of that is Xbox. I numbed the other down that were not unimportant. And then a bit of that is Blizzard. And so that's kind of puzzling, right? Because if these were 3 separate things, why would they release things at the same time? What that means is that we're looking at a single event that's carried out by a number of different network providers out there by a number of different content providers, but all linked to one single asset. And so for everyone that's gone through that, and I think like everybody talked about it in social media, if there's any game that's carried by PlayStation, Xbox, and Blizzard, it can only be Call of Duty. And so here you go. Now, remember, we're looking at 3 different content networks out there. And so that initial problem that we were talking about for just the video service gets compounded by 3, right? It's 3 times more difficult to sort out these issues with the number of people to speak to being multiplied by 3, the number of connectivity providers being multiplied, and so on and so forth. And so usually this is how people figure out that something has happened, right? There's someone on Twitter and maybe he's on that presentation. He says like, oh, I've been looking at this event from a traffic standpoint, and I thought it was DDoS. Well, it appeared it wasn't. And so the next day, the various CDNs or internet exchanges out there says, we've had a big bump. But when chatting with them, most of them weren't really aware of what it was. And so you really don't want Twitter to be your main source of interconnection evaluation, right? Again, proactivity before reactivity. And so, as we've said, subscribers care about OTT services, and ISPs have shown in the recent discussions that I've had with a ton of them that they do care a lot about this. A ton of them actually have ongoing project to measure QoS by favorite user destinations. And so performance and cost, which is the central theme today, is it requires OTT service level monitoring. Like source destination ASNs don't cut it anymore. The other thing to remember out of that is that OTT providers leverage all methods available out there to deliver the traffic. And the bigger they are, the more methods they'll leverage. The last thing is that OTT traffic events, they're now global. And so their impact with every event is hard to scope and to mitigate, right? Global content events over multiple providers. CDNs carry multiple OTTs, and the other way around, OTTs always leverage multiple CDNs. And there's really no taxonomy to delineate. I think someone's pinging me. Am I running out of time? Sorry. And so lastly, the last thing that I wanted to show is bound to this current situation that we're all in. I'm looking at traffic for an ISP here, all blue. It seems kind of normal. And then I kind of like split it in 2. On one end, you have the total inbound traffic, and in green, you have the conferencing traffic. And so it kind of seems bumpy a bit, but not much. But actually, if I remove the entire inbound traffic and I focus on the conferencing traffic, I see that in the last 30 days, it's gone 14x. And so some gaming people might be eating bandwidth that people need to work at home on conferencing traffic. So that's something that I need to keep an eye on, right? Now that the context has changed. And so, but you can look beyond plain traffic and you look at number of unique destination IPs, but basically whatever problem you had with conferencing that would impact 1,700 users 30 days ago now impacts 10,000 users. It's a whole different game, right? And so again, all multiple stages of layered complexity. And I'll stop there because I think I've gone past my time, but this problem gets even more complex if you want to look at performance and cost over all different legs of the delivery chain, from the content to the provider, to the CDN provider, to the connectivity provider, to your POPs, to your last mile POPs, to your different users on different access technologies. And so that'll be it for today. And if anyone has any question, I'll be more than glad to answer them.
All right, Greg, I see one question so far in the chat.
Yep. Let me see. Let me bring up the chat room. Where is it at?
The question is, most of CDNs sitting on operators' networks use operators' IPs as opposed to their own IPs. For such cases, how do you detect whether traffic belongs to Google or Facebook or Netflix?
So I don't want to make this a sales pitch of why we're better at it. I would be more than happy to chat about this with anyone involved. But the idea is for CDNs, there's a variety of data sources out there. Some surveillance data by classic DNS surveillance providers, the routing registry data out there, the knowledge of which ASN is governed by which CDN, and all of that on a daily basis aggregated. And remember, I don't want to spend so much time on it, but basically, Cantic has an idea what your devices see. And if you label stuff through SNMP, because we enrich data from SNMP descriptions, if you say it's a Netflix cache, then I can probably sense that it's a Netflix cache and associate it to the Netflix CDN. If you say it's a Nakamai AANP, then I can probably say that this associated subnet is allocated to us. So it's about being able to compute a large map of CDN to IPs on a daily basis, because things don't change that much throughout the day, based on a variety of increasing data sources. And we add new data sources every day. Does that answer your question?
It was not my question, but that sounds good to me. So thank you, Greg from Cantic. We really appreciate your talk.